Good morning, everybody. Welcome back to the production ESP32 stream. Thank you for joining. We'll give a second here to do a quick technology check. We'll do that in a second. Let's get rolling here. I'm going to mute for just 1 second. Okay, I can see I'm streaming on YouTube because I need to mute it. That's working. Excellent. And let's check LinkedIn real quick. Looks like that is working as well. So for those that joined last time, we had some technology issues right out of the gate that I worked with Restream on. Should all be resolved, hopefully. But again, please thank you for your patience. We're figuring this out as we go. So hopefully it's a better experience than it was last time. Streaming live on X, LinkedIn, and YouTube right now. So those are all the places. If one of those isn't working, maybe switch channels to another one to have a better streaming experience, and we'll continue to tweak and make it better as we're able to. So today we're going to talk about, as you can see on the screen here, flash encryption on the ESP32. And just a couple of disclaimers before I go into this, which is these streams are not meant to be hardcore step-by-step educational videos. It's not polished content. It is me turning on the stream, picking a topic, and I do prepare a few notes of things I want to cover. And then we just kind of work through it together. It's more of like an office hours type format where sometimes I might fumble around and forget stuff. And again, not polished educational content, but hopefully stuff that you can learn from and take something away from it, from the experience that I've had doing this stuff in the past. But sometimes I got to jog my memory because it's been a while. So that's my disclaimer. This is all an extension of the productionesp32.com website where I post things in the blog post here. This is more of like a polished content, thought out stuff to give you information about using ESP32 in production. But anyway, this is an extension of that. And as always, there is a voting section on the page here where you can vote for ideas. Those are starting to come in a little bit. Also happy to take new ideas if you have them of something you want to see on the stream. It is very early days, so it would be very easy to suggest a topic and have me do a stream on it. And so I just had a guy reach out on YouTube asking about Arduino Core from the ESP32. So I may do a stream on that. But like I said, today we're talking about flash encryption, which is now not the top. It was the top when I planned this episode out. Now it looks like OTA anti-rollback has moved to the top slot of interest. And so anyway, this is the way you can vote for what we cover next. But today we're going to be talking about flash encryption. So really quick, one more tech check before we move on. And that's just to see if we've got chat coming through. Looks like it. Shoaib, looks like you're on X. Great. And you tested YouTube as well. Hey, thanks. Appreciate it. I'm going to try text message back, make sure this is working. So, everyone. Okay. And then let's just see if that made it through. Again, I appreciate your patience. Yeah, it looks like that's working there. And I have no idea how live chat works on LinkedIn, but if anybody's joining there, wherever you're joining from, welcome. Okay, so let's jump into flash encryption on ESP32. So first and foremost, I don't want to be the RTFM guy here, but reading the manual, Espressif's done a really good job of documenting the IDF. And there are, warts and hiccups here and there in the documentation or grammar problems, but by and large, the documentation is really good. And for flash encryption, that is especially true. So if you're interested in flash encryption on the ESP32, we're going to cover a bunch of this stuff today, but I highly encourage you to read this page. You can see the scroller here is pretty small. There is a lot of information, but it goes into depth about all of the different things around flash encryption.
And so I'm going to show just a small part of that today. I labeled this Flash Encryption Part 1. I have no idea how many parts there will be, or if they'll be in sequence. Probably not. But anyway, just pointing you to the docs. Lots of good information here. And it's very technical and thorough. You might have to read it a couple of times to really understand it and grok it, as I like to say. But it's all here, very helpful. One thing I will point out for all of this, we're going to be going back to our trusty handy dandy dev kit C here for our coding that we'll be doing today and examples. But the flash encryption eFuses, which control how flash encryption works on the ESP32, varies from chip to chip. And so when you come to the docs page for Espressive, you will see right here I have ESP32 selected. And just to show you an example of this, and that's what we want to be on for this particular one, is we've got this relevant eFuses. You can see I've got 1, 2, 3, 4, 5, 6 eFuses on the base ESP32 that pertain to flash encryption. However, if I were using an ESP32S3, for example, you can see they have all the variants listed here, but I've done this on an S3 as well, and it tripped me up at first because I was looking for eFuses that did not exist, because on the S3, you will notice there are only 4 relevant eFuses. And so just an FYI, as you're looking through the docs here, make sure you have selected the correct chip variant for your project to make sure that you're getting the accurate information around flash encryption. Pretty much everything else around flash encryption is the same, but the eFuses are slightly different, which can control some of the other behavior there. So just something to be aware of. All right, so we're going to go back to ESP32. And let's see, what else do I want to cover here? Yes, let's talk about this really quick. Encrypted partitions. So we're going to switch out of docs boring mode and into fun mode of coding here in just a minute, but just to set some groundwork here. When you enable flash encryption by default, it will enable encryption on several things by default, which is the second stage bootloader, the partition table, the NVS key partition, which is different than the NVS partition. Just need to make that clarification. OTA data and the app type partitions. Now, OTA data, again, slightly different, just like in NVS. There's an NVS key partition, and then there's an NVS partition. In this case, the NVS key partition is encrypted. Same thing with OTA data. You've got 2 partitions where you're toggling back and forth with OTA updates. Those are separate from what's called the OTA data partition, which keeps track of which of those partitions is to be loaded at boot time. So the OTA data partition is encrypted, and then all app type partitions, which then again would be those physical OTA partitions where your updates are running. And then it says other types of data can be encrypted conditionally, and that is any partition marked with the encrypted flag in the partition table. That's just an extra attribute you can add at the end that says encrypted, and then that will also be encrypted. But because these are all encrypted by default, you're more than welcome to add the encrypted flag to those partitions in your partition file, but you don't have to. The other ones you do have to if you want them to be encrypted. So, all right, enough of the docs. Let's switch up here and let's get into it. Okay, let me switch over to my notes here. As we're going through this, I have found that there's anywhere from like a 4 to 15 to 20-second delay, depending on which stream you're on, LinkedIn, YouTube. X seems to be the best for latency, but the chat doesn't really work there. So if you have questions, though, go ahead and put them in the, again, I apologize, I'll figure out X, but LinkedIn and YouTube, I should see that here, and I can address those. So let's hop right into this. Let's just make sure, oh, right at the top of my show notes. Flash encryption is not scary. So this is one of those things. There's flash encryption and secure boot, separate concepts. We're not going to be talking about secure boot. Flash encryption, but both of them like give people a sense of, I don't want to brick my device. And that's the biggest thing I hear from people is I'm worried about bricking the device. So I need to be really careful. You should always be really careful. However, flash encryption, very low
risk. And by low, I mean virtually none. Like I have not, playing with flash encryption, I have not bricked an ESP32 device, which, if we're lucky, means we'll do it today on the stream now that I've said that. But do not worry about bricking your device by playing with flash encryption. It is a very easy to play with feature that you can turn on and then back off again if you need to. You only get a certain number of those, so just FYI, you can't toggle it on and off indefinitely. But you can turn it on, play with it, and then if you want, turn it back off. Hopefully, we'll have time to do that on the stream today, but we'll see how far we make it. But first, right out of the gate, I just want to remove any concern of like this is scary or I'm going to break. I only have one ESP32 device. I'm going to break it. Don't worry about that. Like it's really not as scary as you think. So you can do this. Okay, let's talk about. Let's see how we want to start this. Okay, one other thing I need to cover conceptually, and let's now start looking at code here. So we have our partitions.csv. If you're coming from the Arduino realm, this is hidden away from you. You can select it from a menu of like, do you want a large app with a little bit of storage or a small app with a lot of storage or OTA? And you get to pick like out of the box like 6 different partition layouts. This is one of the other reasons why I always encourage you to go to IDF instead of the Arduino IDE, is because you can use this fancy partitions.csv and you can exactly dictate how you want the flash to be used on your ESP32 device. So that is what I'm using, and that's what I encourage you to use. Even if you're just using a copy of the out-of-the-box ones that Arduino offer, it's nice to see it here so you have an understanding of how your code is laid out on the chip itself. Okay, so this is a very standard one. I've got an NVS partition. This is non-volatile storage. It's separate from the app partitions, but this is where data is stored. Things that go here by default are your Wi-Fi calibration, your Wi-Fi credentials for when you set up go in here by default. A bunch of Bluetooth stuff will go in here if you're using BLE. And what else? I'm sure there's some other things, but it's a separate storage spot. And then we've got, here's this OTA data, which is where we store which OTA partition we're going to boot from. And then you can have N number of OTA partitions, I think up to, don't quote me on this, I think it's like 16 or something, but they're going to be really small if you have that many. Typically you have 2, maybe 3, depending on your app size. These are, as they're labeled here, app partitions, again, encrypted by default. So when we're looking at this, the partitions that are encrypted by default are going to be this OTA data, OTA 0, and OTA 1. NVS is not encrypted by default. And storage, which I have just not doing anything with, but this is where you might have your FATFS or your little fs or SPIFs partition or any other data. This would not be encrypted by default, but you could encrypt it by adding the encrypted flag off to the, let's see, the flags here. So you like, spell it right, encrypted. Okay, but we're not going to do that right now. We're just going to leave it as is. And let's talk briefly about NVS versus flash encryption. They are separate ideas. So while the NVS is a section of your flash, it is not compatible with flash encryption. So the docs clearly call this out. You do not get flash encryption on your NVS partition. You have to enable that as a completely separate concept called NVS encryption, and it does AES encryption. It does it for you, but just beware, it's a separate concept. So when you turn on flash encryption, we'll see this in a minute, we do get NVS by default, but you can disable it and have them be separate things. So just to call that out so you understand that. All right, let's look at our code. I've prepped this a little bit. This is the exact same. Again, I'm pulling this from the Deploy the Fleet SDK Playground project, but it's just a dead simple, we're not even using Deploy the Fleet, we're not doing OTA or anything here. It's just a dead simple program that comes into the main and just says hello from production ESP32 and shows the current firmware version in an infinite loop every 5 seconds. So very simple, very small project. Okay, But as part of that, I do have it connect to Wi-Fi with this little helper method. So I am configuring credentials. And let me just show you that really quick. Hi, menu config. That bigger. Okay. So we're going to come down to component config, and then I have created for this Wi-Fi Connect, I've got the deploy the fleet SDK playground settings. So if I come into this, you'll see I have this Wi-Fi section. And in here, I set my Wi-Fi credentials. So I have this separate IoT network that I use for IoT testing. And for those that get the joke, Juicero2 is the password for that network. So I configure that here in menu config just as a shortcut. Obviously, in an actual production thing, you would never hard code the credentials. You have some other mechanism to prevent. But I just wanted to show you that that is my SSID, SIDNet IoT, and Juicero2 is my password. Excuse me. All right. Now, the other thing I want to show here is, so that's one piece of, I want to lay the groundwork here of why we even do flash encryption in the first place. So I've got my Wi-Fi credentials that will get stored in NVS. And then, just for fun in my code here, I have this super secret key that I've given a text string to. Now, this is a contrived example, but the equivalent to this in a production, and this has happened so many times, you see this in reports all the time, is people putting certificates, device certificates, other API keys, tokens, JOTs, things like that that get built into your firmware. And so this is an example of that. Think of this super secret key as something like a JOT or a certificate or an API key or something that you would definitely not want exposed to anybody. So, Honest, hey, what's up? Thanks for joining. Kabaster, good to see you. I appreciate everybody joining the stream. Looks like a bunch of people are here. Really happy to have you. Those that are just joining, if you have any questions, go ahead and stick them in the chat. Hopefully I will see them. We've had mixed results with Restream getting those to me, but appreciate you being here. Okay, so I've got some data in my binary I don't want anybody to see, and I also don't want anybody to have my SSID and password. If you ever are in the area and you see my SIDNet IoT, you're welcome to join. Okay, so what I'm going to do is I'm going to do idf.py flash monitor. Make sure that this is actually programmed and running on my device. That'll take just a second. Brought some water. Okay, great. Connected to Wi-Fi, that all looks good, and then it's saying like, hello. It's going to repeat this every 5 seconds. Great. Now, from a security standpoint, the reason we want flash encryption is I want to show you what I can now do. And again, this does require, in this case, physical access to the device. But if people know, one of the things they can do is just steal the device, take it back, and then they can get this information later, like your Wi-Fi SSID and password, any of the secrets that you have. And so all of these things just get flashed onto the chip according to that partition table that we just looked at. And if you remember from the last stream, we are set up in a Docker dev container here, so I have access to all of the tools of the IDF. IDF.py is typically what I use to, build flash monitor. But I also have access to ESP tool and all of its commands here, just right in the terminal. And we can use ESP tool to dump the content of flash. And so if we look at our partitions, let's do the NVS partition first. So it starts at 9,000 and it's 4,000 hex in size. I'm going to do ESP tool, and I'm going to do read flash, and I do a start offset. So I'm going to do 9,000 and the length that I want to read, which is 4,000. And I'm going to say this is going to go into nvscontents.bin. I believe that is the command. Let's hit enter and see if it works. Okay, it's reading. And now I've got my NVS contents. So if I click that, I'm going to get a message here in VS Code that says this file is not displayed because it is either binary or using an unsupported text encoding. No problem. As we covered last stream, I have the hex editor installed in my dev container. So I'm going to say open anyway, choose the hex editor. And now I see on the left here just the hex that was dumped. But, you know, the hex editor extension gives me this handy decoded text version. So right out of the gate, it doesn't take me very long to see this sta.ssid, and there is my SSID. Scroll down a little bit more, I've got sta.pswd, my password. And so just from doing a simple flash dump, I can now read in plain text my SSID and password, which is no good. We do not want that to be the case. Okay, so that is a result of not having this data encrypted. And so anybody can look at that and read it and capture that information. Let's close that. Now let's look at our OTA 0, which is where our actual firmware binary program. So let's do the same thing. And really quick, in this partition CSV, you can see that there's an offset and a size. I typically don't like to do it the way I have it right here, which is to do these. I do not specify the offset here, only the size. IDF supports doing that because it will just put it in the next available address, make it this long, the shorthand version, the 1728K, and then this next partition will start wherever that one ends, 10,000 hex aligned for app partitions. And then what I like to do for production, I'm setting a bad example here, is have the hard offsets here so I can know exactly where the offset begins. However, there is a shortcut to figuring this out, and that's to run idf.py partition-table. So I'm going to do that just to show you. And this will actually show me that offset is at 10,000. So really, that should be here. And then the next OTA1 starts at 1C0000. That would, what would the offset would be here, and then it shows where storage is as well. So to read the app partition, I need to have the start address of hex 10,000 and the size of it be, unfortunately, you can't use this shorthand version and the size parameter when you're reading it with ESP tool. And so you just have to calculate it. You use a hex calculator, do 1C, all these zeros minus hex 10,000, and you'll get the size. Did that earlier to save us time. And that's this right here. Okay, so pro tip, let me show this. So I've got the command here is, again, read flash, the offset's 10,000. The size of the OTA 0 partition is this, 1B0000, and I'm going to dump that into app-contents.bin. And you'll notice I added a new param here. This is the baud rate. So I'm going to get rid of that. And I want to just show you the difference. And hopefully you can see it. I know it's at the very bottom of the screen. But I'm going to do just ESP tool read flash. And I'm going to hit enter. And it's going to start reading. And look at this. 1%, 2, 3, 4. It's slow. We're going to be here all day. So don't use that right out of the gate. It's going to take forever, especially if you're doing this a bunch. If you do the baud, I do just 2 million. I think it changes that to some other closest, whatever makes sense UART baud rate, but it makes the baud rate much higher. If you're getting errors reading, you got to pull that back some and make it a smaller number because it's just too fast. There's too much noise on your line, but I've never had an issue using 2 million, and watch the difference. It just churns. So, and that's especially a problem. It didn't matter when we read NVS because that's a small partition. On these big app partitions, 1, 2, 3 megs, especially on the bigger flash size chips, you'll be here all day reading flash. Same goes for programming. You can specify that -B the program. It will cut your programming times way, way down. So, pro tip there. All right, we've got our app contents now. So we're going to open it. And it used Oh, I already had it open from the previous thing. Okay, so it's opened up in hex, and you can start to see some of the strings that are built in. It's got like the build date. This is the IDF version 5.5. It's going to have all of your hard-coded strings from your log. But now if I just do a search for PNWED, you can see right here, it's got our super secret key. Super secret key is also in there because I'm printing it out as that. But the important part is you can see just here in plain text, again, that JOT, that device certificate, that API key. And so be mindful of that. If you're not using flash encryption and you're hard coding these things into your firmware, they are definitely available if anybody reads the flash out. And so from a security standpoint, flash encryption helps us protect against these things so that even with physical access to our device, a hacker or some other nefarious person isn't able to gain access to those things that we would consider private or secret. Okay, let's enable flash encryption on this thing. Now, we talked about eFuses. Let me just cover that really quick. So flash encryption is controlled by eFuses. Another very scary topic for people. They're like, oh, eFuses, I burn them and then I'm stuck. True in some cases, not true in other cases. For the flash encryption, we're going to let the menu config and IDF handle it for us. And so I'll show you what that means. But just as a general good to know, you can run idf.py efuse-summary, and it's going to connect and read all of the eFuses on the chip. And so the ones that we care about, some of these disable DL encrypt, again, disable flash encryption and UART bootloader. And again, all of these, if you want to know more information about all these eFuses, read the docs. They're explained. You're going to have to read it 2 or 3 times because it takes a little bit to wrap your head around it. Flash encrypt config, and then here is the important one that we're going to look at. Flash crypt count. Again, this is named slightly different if you're using an S3. I haven't looked at it. Some of the other variants. Read the docs, you'll see what it is. And then the note here is super helpful. Flash encryption is enabled if this field has and this is carries over, an odd number of bits set. So just, you can only set the bits so many times until the eFuse is completely full. So it has, what is this? 8? 7 bits. And so if you burn the eFuse to set 1 bit, that will now be an odd number of bits, which means flash encryption is enabled. So everything else in the ESP32, in the bootloader and everything, is going to assume flash encryption and change its behavior to account for that. If you burn another bit in that eFuse, so it would be 1, 1 at the end, that would be an even number of bits. Flash encryption is disabled. And so that's how you can turn it off and on several times until you run out of bits. Once you run out of bits, you can't, you're stuck. And because it's 7 bits wide, once you've burned all of them, now you're stuck. It's an odd number of bits. You can't make it be an even number of bits again. And so flash encryption at that point is enabled forever. And if you didn't want it to be, well, you had several chances to get it right and failed. So now you're stuck. But you have some leeway between now and then. For a production setting, what I would recommend is in the factory programming for this, you're going to want to have a script that burns all of them. So you don't want to just you don't want to just set the first bit, because then if somebody has access to set the eFuse, they can disable flash encryption. It's not just that easy, and then they can read everything, but you're still leaving leeway for somebody to change the encryption state. So the safe practice there is just burn them all. 1, 1, 1, 1, 1, 1, and then flash encryption is enabled and physically cannot be disabled for that device. So that's a production tip. Okay, so now let's go to actually enabling flash encryption. Talk about the modes. So it's actually not very difficult at all, and there's 2 modes for this. There is development mode and there is release mode. Now, release mode is the mode that can get a little scary because if you go full release mode, you completely disable the ability to flash new firmware over the UART. And we're not going to cover that. That's a more advanced in the future. We're going to be playing in the safe area today, which is development mode, which is the flash is fully encrypted, but you can still from the command line flash new binaries without any issue. And so let's take that. Okay, so to do that, we're going to come into, well, first of all, we have to do some prep work, which is, well, we'll get there. Let's take it one step at a time. Check in on chat here. Yeah, Capacitor, it's the same. So once you burn a bit, it's that bit is burned, and so you can still burn more to turn it on and off. But yes, so remember, eFuses, yes, scary, but not so scary for flashing. So okay, so we're going to come into, let's make this a little bigger so we can see. All right, so to control flash encryption, we're going to look at security features. But before we do that, we're going to come into component config. We're going to scroll all the way down here to NVS, because I remember I said earlier, NVS and flash encryption are two separate concepts. If I come into NVS, I have no ability to do flash encryption here. And that's because even though they're separate concepts, NVS encryption depends on flash encryption being enabled because you have to have an AES encryption key for NVS encryption, which needs to reside on an encrypted partition of its own. That was a huge mouthful. I'm going to say that one more time. NVS encryption relies on flash encryption being enabled because the key that handles encryption and decryption for NVS has to be stored on an encrypted flash partition, which is separate. So that's why I don't have any option here to enable that. So let's come back to security features. And you can see required signed app images. That's secure boot. We're not going to be messing with that. Enable hardware. Sorry, that's a version of secure boot. We'll talk about that completely separate, different stream. Then I've got enable flash encryption on boot. Big caps, read docs first, which again makes it sound scarier than it is. We're going to be okay. All right, and then that opens up some other options here. We're going to leave these enabled down here. And then you can see enable usage mode, development, not secure. We're going to go into that, and I can change it to release mode. And again, read the docs on the differences. Right now, we're going to stay in development mode. And then you have this potentially insecure options, which is this leave UART bootloader encryption enabled. This is part of development mode, which allows us to, even after we've enabled flash encryption, to continue to flash devices over the UART. And so the reason that's insecure is even with flash encryption enabled, somebody could come over and flash their own malicious firmware, and it's going to encrypt just fine and make sure it's encrypted and secure, but then it's running somebody else's firmware. And that's something that you can either disable that here to prevent that, but secure boot is really the security feature that helps with protecting against that. So we're just going to leave all the defaults as they are set for development mode. One thing I want to talk about really quickly, read more in the docs about this, is the way you generate a key for flash encryption, which looks like, is that Febby? Febby has perfectly segued this with a question in the chat. Does that mean every encryption key is different for every device? Exactly what I want to talk about. In this default setup, yes. What will happen is we are enabling flash encryption, and that involves a change to the bootloader, the second stage bootloader, and then our app as well will be flash encrypted on flash. But encrypted how? And so there's two ways to generate a key. The first way to generate a key is to have the device do it itself. So the ESP32 will generate its own flash encryption key and use that to encrypt flash. Again, separate from NVS. Talk about that more in a second. that means every single device is going to have a unique one. So if somebody somehow brute force figures out the flash encryption key on one device, the only device that they have access to flash wise is that device. The other thing that you can do is generate a flash encryption key, and you can burn the eFuse with that and have it the same for every device. This is the insecure, not recommended way to do this. But what it does allow you to do is pre-encrypt the firmware before you flash it. And again, that's not what I would recommend. I would let every single device have their own, then let the chip do the encryption, which over UART it will do, and then through OTAs it handles seamlessly for you as well. So the OTA update would come in normal binary, not encrypted in any way, secure over HTTPS, so you can't read it as a man in the middle, and then before it writes it to flash, the ESP32 itself encrypts it. That's how that works. So those are the two different key mechanisms. Okay, so now we've left these settings all the way that we have them, just by default. We've got it enabled, but now let's come back to component config. I'm down to NVS. We're running so short on time. I got to speed this up. A lot to cover. Just as I'm going through, there's a lot to this. I want to make sure we understand. Now you can see enable NVS encryption is an option and it's checked. So just something to be aware of in IDF, at least in 5.5 of the IDF, when you enable flash encryption, it enables NVS encryption by default. And so that's just something to be aware of. We've got, let's see, am I ever covered that? Pure engineering. No, no worries being late. If you got a question, drop it in the chat. I'll come back to it, and even if I've already covered it, I'll cover it again. Okay, so now that we have those things enabled, we're going to get from these settings, we're going to get NVS encryption and we're going to get flash encryption. Okay, so I'm going to come out of here and I'm going to save the configuration. I'm going to do an idf.py full clean, which cleans my build environment. And then I'm not going to build and flash this yet because, again, for flash encryption to work, we need to have an NVS keys partition for our our AES key for NVS encryption. So let me just make sure I get the syntax right. I'm just going to grab one from another project so that we can save a little bit of time. I don't have it in here yet. Okay. Yes. I'm going to grab that. Paste it in here. So I didn't test this beforehand, so we might be going on an adventure here. From the docs, it says the partition size for the NVS key partition needs to be 4K. And just a general thing to know is these app partitions have to be 10K aligned. And so if you're, just as a contrived example, if you made the size of the partition less than 10K, it doesn't matter. OTA 1 will be at least 10K down because they have to be 10K hex, sorry, 10,000 hex aligned, which I believe is 64K bytes. So, but if we look at this and we do our partition table again, you will see that this OTA data starts at D00 is 8K in size, hex 2000, but the OTA partition starts at 10,000. So let me just bring up our calculator in hex mode. And if we do a D000, we do plus 2,000 hex, you can see we end up at F000. Now, again, the app partition can't start there because it has to be 10,000 hex aligned. And so if we do 1,000 hex minus F0, you can see we have hex 1,000 in between the partitions, which, if we look at our decimal, I know that's kind of small, but that's 4K. So I think we have enough room to squeeze in our NVS keys partition right between our OTA data and our OTA 0 partition. Anytime you change partition table, wipe the device, you got to redo the bootloader, like everything changed. So I'm going to copy this in and we're going to realign it here. So we need this NVS key partition. It's of type data of subtype NVS keys. The offset is going to be F000. We're going to make it 1000. And then I have encrypted here in this other project as a flag, but remember, it's encrypted by default. So you don't, this is redundant. You don't need this. I like putting it on all the ones just so if anybody looks at it and isn't familiar, they can just at a glance. They don't need the knowledge of the IDF to say, oh, I know which ones are encrypted by default. It's very explicit. These are the partitions on the flash that aren't. And so it doesn't hurt, even on the ones that are encrypted, it doesn't hurt to add the flag encrypted. I'm going to save that. And then I'm going to do an idf.py build. I have never tried to do this live. We will see what our chances of having this work first time out of the box. Yes, encryption algorithm for flash encryption. Yes, AES. I believe that's how. Sorry, for NVS, it's definitely AES. I believe that's also the same algorithm for the flash encryption. And as I mentioned earlier in the stream, the docs are amazing. Flash encryption here. I'm going to scroll all the way down, and they actually have a section. There you go. AES 256. They describe in detail how the flash encryption algorithm works if you want to nerd out on it. So there you go. Okay, we got to build failure. Because why? A bootloader binary can be maximum. Ah, yes. Okay, great. I'm glad I got this here because I wanted to bring this up, but I forgot that it happens. Bootloader binary is 9030 hex bytes, too large for partition table offset 8000. Bootloader binary can be a maximum of 7000 hex, and unless you increase the partition table offset of the sorry, unless you change the partition offset of the bootloader. And so I don't want to do that right now. You can, so basically the problem is saying we're starting our partitions here at 9000 offset. There's a bunch of stuff stored before that, like the bootloader. Enabling flash encryption increases the size of the second stage bootloader. So by default, it no longer fits into the size there. And so what you can do, I'm trying to decide what we gloss over and what we cover. Let's just keep digging, and if we have to break this into 2 streams, we will. We'll do our best. We're gonna do menu config. Pro tip, in menu config, if you use the /, it opens up a fuzzy search. And so we're gonna do that. There you go. Bootloader offset in flash. Okay, as you can see, by default, that's 1000. And then also right here, partition table offset is hex 8000. Right up here, we can see our first defined partition is the NVS partition at 9000, which means the partition table takes up 4K, hex 1000, and it's located at 8000 and ends right, at 7 FFF. Sorry, at 8 FFF, right before 9000. The bootloader starts at 1000 and occupies hex 1000 to hex 8000. So it has to be at least hex 7000 or smaller, but by enabling flash encryption, we've made it too big for that. So that's the error that we're getting. Okay, and it tells us very specifically the size of it is 9030. And bring back our calculator. And that's in hex, so 9030, it can only be 7000, which means we're like 8K too big to fit. And so what you can do with menu config is you can slide all of your partitions down. We're not going to do that. We're going to take a shortcut. And so let's take our shortcut. And we're going to come into idf.py, menu config. We're going to come into the bootloader config, and we're going to come into log. So we might be able to, it's already built for size, so that's not the way. The way I typically do this is I come into log, and my bootloader log verbosity is info. I can change that to warning. Let's change it to warning. We might have to go all the way to error. I can't remember. But let's just do a build and see what we get. Okay, now we're down to 8170. So you see, we got like halfway there with that. Hopefully, it's still true with IDF 5.5. It was in all of the previous versions that I've messed with this on. If we change this to error, I think we'll be fine. The unfortunate part about doing this is we're not going to see all of the super helpful logging in the second stage bootloader, because it will log info of what it's doing, what eFuses it's burning, that it's encrypting your flash, and all this other stuff. We're not going to see that, but let's see if that actually got us to where we needed to be. Oh, it didn't. 7C40 is too large for partition table auth. We are just ever so slightly too big now. C40 too big. What is that? About 3K. We're about 3K too big. All right, let's just change it to none. Should have tested this beforehand. Like I said, I've always gotten around this by just changing the log velocity, so they must have made some changes. Yeah. Yes. Okay. We made it. Well, I don't have time. We could go back and look through and see how big our bootloader is now. But now we're getting no bootloader output. Again, the way you would typically do this well, it depends on production, because you don't really care about the bootloader output once you've gotten to a production level, typically. But again, the way you handle this is you slide those partitions down, you rearrange some sizes. I'm not going to mess with that right now, but now we're all set. Okay, the other thing that we need to make sure we do for this to work is we must make sure that the NVS keys partition, this one right here, is completely empty. And the reason for that is because if there's anything there, the ESP32 is just going to assume that it's the key, even if it's complete garbage. And so it's going to be like, oh, I already have an NVS encryption key, and this is what it is, but that's not really the key. And so you want to make sure that that is empty. The way you can do that is using ESP tool. And we're going to say erase region F000 and that size. So we're going to erase our NVS key region. So let's do that. The other thing we need to do here, and this is just, I've learned this, where I've enabled flash encryption, and then I dump everything like I did at the very start of the stream, and then I'm like, oh, what the heck, I can still see secrets. And that's because when it flashes, it overwrites different areas. So yes, you need to make sure that the NVS key partition is clear, but you also want to make sure that the NVS partition is clear, because it will be encrypting, but it may still have fragments from when it was not encrypted. And so let's just do, I think it's just erase flash. This should erase everything. And it's going to take a while because I forgot to set the baud rate to 2 million. Oh, it didn't take too long. Okay, great. Chip erase complete. Right now, our chip should be completely empty. We should be enabled. And then let's just do history or prep summary. Yeah, ESP fuse summary. Let's take a look at this again really quick. You're going to see our flash crypt count is still 0. Again, we've turned the setting on in IDF in menu config, which means once we flash it and it does a first run, it's going to encrypt everything. And then we should see this change. So fingers crossed here. Now that we've done all of that, let me just really quick hit the docs, make sure I haven't missed anything. I don't think we're going to do an idf.py flash monitor. The very first time it does flash encryption, this will happen on the factory floor typically. Depending on how much flash you have and how many partitions you're encrypting, there will be a delay. And a significant delay when it comes to doing this for tens of thousands of devices. Flash encryption can take, up to a minute, 2 minutes on some of the bigger, like 16 meg flash versions. So it's got to go through and encrypt those partitions one at a time. And there is some time overhead to that. That's why some people like to do the generated key because they can pre-encrypt. I still hesitate to recommend that. Let the ESP32 and then figure out who pays that tax for flash encryption. It could even be the customer out of the box. It takes a minute to boot up. But anyway, discussion for another time. IDF.py flash monitor. Let's see what we get. All right. Let me come back, see if I got any questions. All right. I assume we're still pretty, yeah. My restream is showing like 10 minutes behind. I assume the streams are pretty current. Okay, now we're in like a boot loop here. So let's turn this off and see what happened. What did I say at the beginning? I've never bricked a device doing this. Failed to read NVS security config. Failed to generate keys. Okay. Should be dumping our key into here. Should generate that for us. Trying to think if there was something else that we needed to do out of the box to make sure that key should have been generated for us, but like this is normal, but then it should generate the I know we're supposed to be done in 8 minutes. I'm not turning this stream off until a fatal error has occurred. Active security features detected. Erasing flash is disabled as a safety measure. Use forced override. Okay, let's go back to our eFuse summary. And let's look at how this has changed. You can see, I don't know if you remember before, this was all zeros, like this was. But now you can see flash encryption key. It's given us a flash encryption key. So that's great right there. And if we come up to our flash crypt count, you can now see that the bootloader itself noticed that we enabled flash encryption, so it turned it on. And now we have one of the bits set. So we have an odd number of bits, which means flash encryption is enabled. And so I'm actually glad this has happened because, again, this is where like the panic starts to strike and you're like, oh my goodness, what have I just done? Don't worry, I'm not panicked yet. A little bit panicked, not much. Okay, so flash encryption is all enabled. It looks like the bootloader did its job, but for some reason NVS encryption is having an issue because it's saying it can't generate the keys. And so let's do ESP tool, trace region. Again, this is for NVS, not for flash. Flash encryption is that key is burned into its own eFuse. The NVS encryption key is burned into the flash, the NVS key partition. And so this one you can actually delete and recreate, and it'll reconstruct your NVS. So that shouldn't be a problem. So I'm not sure why we erase the whole flash. I think I'm going to get the same error. As I said at the beginning of this stream, not polished educational content. All right, let's do monitor. See if we're still like repeatedly crashing. R. Okay. Reconnect. And it's the same. I'm assuming it's the same error. Yes. All right, so let's come back up to here. Look at NVS Flash init. This should, if we come into this, you can see config NVS encryption, like it should handle failed to read security, generating NVS encryption keys. You can see that's what we're getting here. Failed to read NVS security config, generating NVS encryption key. And then it's saying failed to generate encryption key, invalid arg. So let's just, let's dig into it, see what's going on. All right. Failed to generate, and that's because we're getting invalid arg. So let's come down into here. If schema config is null pointer or config is null pointer, or schema config NVS flash key gen is null pointer, return invalid arg, which is the error we're getting. But then we also, because it needs to have a function to do keygen, because then it's just calling that function here. So my guess is that this is what we're hitting. I believe we should be able to see that if we theme config NVS flash keygen is null pointer to I don't know if I can log from here, but I have logging set up. For those that were hoping this would be over in 3 minutes, it's not going to be. So you're welcome to stay longer if you got a job. No worries. But we're going to learn together here. Okay. Let's see if that will work. I'm not. This brings us to another piece of learning that we have to do. I can now, well, let me actually just show it. Let's make a bad problem worse by doing idf.py flash monitor. And let me show you what happened, what I think should happen. I'm in a hole, why not dig it deeper? That's what I say. And hopefully this will at the end have the effect of making you less scared of doing this, not more scared. Yes, perfect. That's exactly what I wanted to happen. Great. Yeah, I know stuff. All right. You can see I just did an idf.py flash monitor and I'm getting this invalid header, blah, 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 blah. The docs actually cover a bunch of the failure modes of flash encryption, and they do cover this. This is another one of those panic moments when you're first doing it where you're like, I've bricked my device, time to go to the forums. You have not. We have, like we just proved with our fuse settings, we have flash encryption enabled. Fuse is burnt, one of the bits is set, we have a key in there. And so we can no longer just do idf.py flash, because idf.py flash does an unencrypted flash. And that's not what we want. Now we need to do encrypted flash. And so there's two commands that now become your friend once you have enabled flash encryption. And that's idf.py encrypted flash and idf.py encrypted app flash. Let's just do a -h here, or a dash. You can see from, here we go. Encrypted flash will flash the entire thing, the bootloader and your app. Encrypted app flash will just flash your app, the OTA partition. And so I typically do encrypted app flash because it's very rare that I would need to rewrite the bootloader, reflash the bootloader. So now we come back in here, we can do idf.py. I may have overwritten the bootloader as well. So let's do, for this one, let's do encrypted underscore dash. Spelled encrypted. Encrypted flash monitor. Got to plug my device in. Okay. All right. If anybody has commented on LinkedIn, I apologize. Those are not coming through to Restream. If anybody's on LinkedIn and would like to test that and send a comment, I'll find it later. I'm just trying to work out the bugs there. Okay, cancel that. And okay, check it out. This is our problem. So this schema config is null, which we should not have to specify. So let's go back in time up here. So it's doing our schema config. Read security config v2. Oh, that's what we're doing. Jumped in. That fails. ES config default security. So let's look at this. I mean, I'm not sure how that would ever get set. I have not done this in the latest version of IDF. Maybe there's a new hoop you have to jump through. But I mean, clearly, this is where we're setting up the default schema config. Let's just do a search in this file for default. We pass it in there. Register security scheme. So this is how it would get set. Not coupled anywhere. With the scheme config. As it stands, we're doing flash init. It's taking our config. That's our config, but we're looking at this nvsec default scheme config, which I would expect set for us. Never set that before. Right out of the gate, it's saying if you don't have it set, you're not getting it. Okay, so let's look at oh, it's saying, hey, Capister's coming in with the Chat GPT answer. Let's try it. I was gonna read the docs, but let's just go Chat GPT on this. Okay, make this out. Apparently, there's another setting that I missed, which is NVS key partition. So let's do security features. Oh no, we're gonna go to NVS. Sorry. Okay. Component config. NVS. When same key is reused for different data types. NVS. See, this is legacy. Flag compatible with old versions. We shouldn't need that. You're saying enable NVS key partition. Let's just do a search for NVS. NVS encryption. We're using a custom thing. Capister, I don't think that's it. I don't see that setting. Storage. This should be all we need. We'll switch this NVS set. We should just be able to straight an it. There. Okay. No, we don't want to do that. Development mode. Enable flash encryption on boot. Select encryption mode. Select UART download. Select the log verbosity and flash it. Flash encryption. Flash. Secure flash encryption enabled. Secure flash enabled. What we've got. Yes. Secure flash encryption mode. Development is correct. Encrypt only the app image that is present. Okay, yeah, that doesn't. Okay, flash encryption enabled. Skip right. Require flash encryption to already be enabled. No. None of these are it. I swear I've just found an edge case of this should work out. I've never had to do anything special to enable this other than just call NVS partition and like this, sorry, back here in main, NVS flash init. Like that should be all we have to do. That should be all we have to do. Let's see. We're learning something on the fly here. We could do init secure init partition, but we shouldn't have to. It should take care of it for us. NVS flash execute. I'm worried. So I'm looking at another project, sorry, off on the side here that I have this in. And in a previous version, this was V1, not V2. Like, sorry, it didn't say V2. It just said NVS Flash read security config, period. Not a V2 version of it. So feels like we're missing some piece of configuration because it's going to read the flash config based on a function that we have not defined. So, okay, check it out. This is the way we're going to solve this. Come back. And typically in the docs, they will link you to a sample project. Let's try and find that. Flash encryption. We can always just go to. There we go. Okay. Main. Flash encrypt main. NVS Flash init. See, they're doing the same thing we are doing. And so we don't have a custom partition here, which you would have to do if you wanted to initialize your own. But we should just be able to call. See, and so same thing here. You see this? They're doing NVS Flash read security config, but the IDF itself is trying to do NVS Flash read security config v2. So this is new. Okay. Let's my polished streamer in me is like, guys, let me go figure this out and I'll come back and tell you what it was. Which, for those that are not interested in watching me fumble, thank you so much for joining. You're welcome to get back to your productive day. But I think there's value in digging down to this because that's how I learn more. So if you want to stick around and go through that journey with me, let's do it. But I am going to stay. I'm going to stay the path. I'm gonna keep streaming this until the sun goes down if I have to figure this out. So, what is this v2? And it's saying that we already have to have a scheme config, right? This, which has a function on it. And the only place I can see that getting set, in this file anyway, scheme config. That's the default. And again, the default here is just going to be a struct. So like nothing's defined here. And this read config, if we go a step further, it's just going to be a function prototype. So great. And so now we're reading it here, and that's where we are. We're in Flash init. Great. And it's failing. And then we're trying to generate. So it also doesn't have the generate function. So we're missing both functions. We're missing the read function and the generate function. Okay. Somehow we have to get those. And the only way I can see that is for it to copy into this scheme config. And this scheme config has to be defined somewhere. Let's start there and see if the docs help us with it. I am on 5.5. Let's take a look at see if we great. Anything else on this page? Reference. Callback function prototype. Yep. But why isn't it? NVS Flash secure init. Initialize the default NVS edition. We're calling Flash init. Sorry, let's come back up. Yeah, right. So we're calling Flash init from our code, but it does call Flash secure init eventually with the config. The problem is we're not making it that far. We're dying right here. Okay. Same thing. Registers the given security scheme. Well, that's great. but they should provide us. They should provide those out of the box for us. That's the whole point. Generate and store the NVS key, specified key. How do we set up this security scheme? Oh, that function. Yep. There. Yeah. Storage, large amount of data, keys and values, namespaces, NVS iterators, NVS encryption. Please refer to the NVS encryption guide for more details. And it's the structure. We've got the NVS key partition. This partition should be marked as encrypted, and its size should be the minimum partition, 4K. I've done. When NVS encryption is enabled, the NVS flash init API function can be used to initialize the encrypted default NVS partition. The API function internally generates the XTS encryption keys on the ESP chip. The API function finds the first NVS key partition, automatically generates and stores the NVS keys in the partition by making use of the NVS flash generate keys API function provided by nvsflash.h. That is just not happening. Expressive. I think this is just a bug. This feels like a bug. I'm not doing a custom partition. I'm doing the component NVSSec provider stores all of the implementation specific code for the NVS encryption scheme and would also accommodate any future schemas. This component acts as an interface to the NVS flash component for the handling of encryption keys. NVSSec provider has a configuration menu of its own based on which the selected security scheme and corresponding settings are registered for the NVS flash component. Okay, now we're getting somewhere. Now we're getting, looks like we have to register a schema. That would make sense. Although again, I would expect them to do some stuff for us out of the box here. So let's open that file as well. This is NVS Flash, just a header file, as is this, but in schema, so we can protect the NVS encryption keys using flash encryption, which is indeed what we want to do. We can protect it using HMAC peripheral, which we do not want to do. NVSSec provider config flash encryption default. Okay. It feels like we're missing this, like some registration that is not happening, that they're failing to handle for us. Okay. So it feels like we should be NVSSec default schema config. Yeah. then it's trying to use that first argument, schema config. It's trying to do flash key in. Okay. All right. Let's do really quick before we do that. We're going to take this and we're going to come down here. Slash expressive if come to issues. We're going to straight search for that. This was opened on June 6th. This, I believe, is the error. Nothing. Back to this. Breaking changes in ID of 6. No. That might have something. That's 2020. S3, generate the key, encrypt the files, merge. Your boot, no. Oh, no, no. Oh, no. On. Okay, let's come back to the example. So all these examples will have a defaults. And sometimes they set some extra things here. I'm not seeing anything there. Yeah, I'm not seeing anything there. Okay. Let's just do a search for ski. Find apps. This shouldn't matter. Okay, let's do a search for link. NVS encryption is enabled. Nothing. Secure flash encryption. Where are these settings? Come back to that. Where are these settings? Security feed. Enable flash encryption on first boot. So we're in security feed. All the stuff in red is we don't have access to either because other settings don't allow it or the chip doesn't allow it. Okay. Parth, welcome. It's late. Hey, thanks for jumping on. You've reached the black hole portion of the stream where we are in a deep, dark hole of not getting flash encryption to work. We have not bricked the device. I would like to point that out for all of you that have been here from the beginning, as I promised we would not. But we can't get flash encryption to work in IDF 5.5, and I'm like heavily leaning on this being a bug on their side because we're calling it as the documentation says we should. And so, like I said, I'm just going to keep going until we figure this out. And for those that are still hanging in there watching this and want to be helpful, feel free to comment. The problem we have is we're calling NVS flash init. We do have config NVS encryption enabled, so it should be coming into here, which we have proven it is. It is failing to read the config, not for the reason that the config doesn't exist, but because the function this is trying to call doesn't exist. And then it says generating keys, and then this fails. And the reason this is failing also is because if we come into here, it's trying to call a function called NVS flash keygen. Well, it's really up here. This function doesn't exist on our schema config, and our schema config is not something that we at an application level should have had to set up at all. And so we're either missing a setting somewhere or some initialization function call, and I haven't found it yet. So you're all caught up. So that's where we are. And it's because, yeah, so we call with void. So our application has no idea that there is a security default scheme, but it does. It's static. And remind me again how it's getting set. Set default. Right here, NVS flash register security scheme. Copy that. Go down to IDF. Search for it. And then GitHub does this, which is so awesome, which says, like, I don't know what you're talking about. Even though, like, you definitely do. We're on 5.5 of the code. Yeah, this is funny how they do. Not components. NVS flash. Source. You can see that I have found in the code NVS flash register security scheme exists. But if I search the entire repo with GitHub, repo ESP32 for that same thing, it's like, psych, that doesn't exist anywhere. Code has ... Sign in. Oh, I'm in. Yep. Okay. Okay, GitHub, you in. You grab a. And I stream from a private window just so it doesn't. Other things. Bring this back over. I'm logged in now. Extern. Components. NVS security provider. Okay, let's come into here. NVS security provider register flash encryption. Feels like it should be calling this internally. Because now, look at this. Yeah, see right here. This is where it's setting the schemes. Setting the functions on the security scheme. Setting that we're missing NVS flash keygen. We're also missing NVS flash read config. And that's getting set right here. And it needs to, because they support multiple flash encryption mechanisms, which we found by looking at the code. There's flash encryption and there's HMAC. You have to say which one you want to use. And so it seems like we need to call this with NVS. Yeah, it seems like Espressive has not wired things up the way they should have out of the box. That's what I'm seeing here. And that's how we get scheme config set up. Okay, let's just start modifying the IDF. Let's right up here on flash init. Let's call this function. Let's see if it'll take like will. Okay, what is this all gated up? SOC NVSSEC key protect using. All right, let's look for that. NVSSEC key protect. Not getting anything. Okay. Because there is another component for key security. We can CMake lists. We should not have to include anything else. What was the other one? Found it in the docs. NVSSEC provider. So one thing that this is reminding me of, Aaron, not sure if I pronounced that right. If I didn't, I apologize. That's where we're headed. So one thing, as part of my production obsession, is I have a CMake list that's modified, and I have this set components main. And I have a little note here that says, be explicit here, otherwise the entirety of the IDF is built, even if you are only using a small piece of it. This also forces you to keep track of every dependency you have, helps reduce build time. I put this on all of my projects, and so I only ever include by default what I need. If you take that out, it'll build everything and makes the build longer. But I think what we might have uncovered here is that the IDF build system may not be including something that it should, even though you haven't explicitly asked for it and shouldn't have to. But let's come back into menu config and see if look at that. Now we have it. Okay. Guys and gals, and anybody that's watching in between, let's try to flash this again. Plug the device back. Now it seems like it's using the default flash encryption mechanism. Now it should be able to read the config. Now it should be able to set the config. And if this works, so help me. Did it. Persistence. Follow your dreams. Okay. I will be logging a bug with IDF on this. Okay. So the other way we could have accomplished this is removing this set components main. Again, if you don't set components explicitly, the entirety of the IDF is built into your project. This makes your builds longer. It makes your binaries bigger for things that you're not even using. So I always recommend you do set components, explicit components. Now, IDF, when you enable certain features, should on its own include those components. And so somewhere in the IDF CMake build system, when you enable flash encryption in IDF 5.5, I don't know how far back this may go, it is not including by default. I'm pretty sure it's this. I added both of them. I'm almost positive it's this NVSSEC provider component. It is not including that on its own, which it 100% should. I should not have to include this because they have created an abstraction layer for me that should properly handle. So I will log a bug for this, and see what they say. But the point of all of this, so we can end the stream like 40 minutes late, is that we are now running in a flash encrypted mode. And so I would like to point out briefly, for those that have been in this long, long journey, I promised no bricking, and I have delivered on that promise. It's not scary. And, you know, sometimes you got to dig in and figure it out. All right, we started this stream with exporting our flash and showing that our secrets were available and visible. If you remember, app contents bin had our what did it was owned, however you pronounce it. That's our secret there that we want to see. And then our NVS contents has our password. So now, or grep. What was it? Now we're going to do ESP tool.py read flash 0x9000 to a length of 4000. We're going to say NVS contents encrypted.bin. And I can't remember if I erased. If not, I will do this again and show you that it truly is encrypted. But let's export that again. And now let's open up our NVS contents encrypted binary. And now we're seeing a lot of garbage in here. And so now if I do a search for SIDNet, I should not find anything. That's correct. And my password, if you remember, was Juicero. No results. Perfect. Okay. It only took an hour and a half, people. No, really, this, once you know, and now that you've been through it, turning on flash encryption, 10-minute process, not a big deal. Okay, but as you can see, neither my SSID nor my password are now visible when I dump the flash. NVS encryption is working. Just as a reminder again, NVS encryption is handled separately, but in connection with flash encryption. Okay, so we're covered there. The other secret that we had was in our app contents, which was our super secret key. In my case, just that string. And so let's do a dump of 10,000. I believe it was like 1B that. We also have to add our 2 million baud to make this not super slow. 6. And we're going to call this app contents encrypted. Let's dump that. Okay, so while that's dumping app contents, you can see right out of the gate, you can see all these strings that are included in your firmware. So SDK playground, all this other system time, all that. So now let's take a look at the app contents encrypted version. Now, you know, we're seeing letters, numbers, characters, but this all looks just like a bunch of nonsense. So over here in app contents bin, if I do a search for app content, wait, there we go. Just do a search for IGOT was part of the thing. And then let's go to our encrypted version of that. Do a search for IGOT, and you will see no results. So, whew, thanks for coming along on the journey there. That was a party. It was great to do that. I actually really enjoyed going through that. I love figuring things like this out because these are the types of things that a lot of people will struggle with and give up and go way, way down the rabbit hole. But again, I hope that was instructive to see. We did a bunch of things there. First, again, from last stream, we set up, we're developing in a dev container. And so out of the box, VS Code allows us to do cool things like go to definition of all these functions down in the IDF. And so we found out, hey, read security config and generate keys is trying to call a function on a struct that we have not set up. And so that was cool. To verify that that was the problem, I modified the code in the IDF to print out some extra logging. So we were able to do that. These are all things that you will for sure 100% guaranteed have to do if you are making a production project with ESP32. These are just things you run into. you figure out. And so I like this setup because it allows me to do that pretty well. Kind of a mix of VS Code, digging in, checking the IDF, checking issues, reading the docs. This is part of it. So, all right. And so what we found was, in my case, set components main was excluding the NVS security provider component, which must be there so that the build of your project correctly includes the definition for some structs that you should not have any idea exist because they are abstracted away from you under the NVS um, under the NVS abstraction. So, all right, that is going to do it for the stream today. I will be back on Friday. I know I said my schedule was Monday, Wednesday, Friday, 10 a.m. Mountain Time. However, I do have an engagement Friday morning, so the stream will be a little bit later, probably noon, but I will post on social media like the exact schedule. So probably 2 hours later than normal. I do apologize. I know some of you are joining from the other side of the world where it is already very late, and I just said it's going to be even later. So I apologize for that, but you can always check the recording afterwards. It stays up on all those social platforms. So that is going to do it. Again, if you want to vote for content, head over to productionesp32.com where you'll get blog posts about stuff that I'm figuring out and learning and tips for production use. And then you've got this vote for the next stream page, which has a list of ideas. If you don't see the idea, you can email me support@productionesp32.com or kevin@productionesp32.com. They go to the same mailbox, and I will add it to the list so people can upvote it, and we'll pick what's next. I think we're going to take Flash Encryption Part 1 and call it good. I don't think we'll do Flash Encryption again on Friday. OTA anti-rollback, I've started looking at. I know it's top of the list. I know it's what most people have voted for. I want to do a little bit more research there to make that stream valuable and not just me fumbling around. And also, like the real reason is I'm partial to this one. I haven't voted. You know what? I'm voting for it right now. Voted for. It's now tied for first. So I guess we're gonna have to do that one on Friday now. I do want to play with this SSH server. They did a port of libSSHD, and so you can actually SSH into your ESP32. I'd kind of like to just go through setting that up and see what that's all about and do some learning around that. So somewhere around there, Friday is what we're going to do, whether it's SSH or something else. Thank you so much for joining. I really appreciate everybody being here and hanging with me through all of that. Hope you learned something. And again, if you have questions, comments, anything like that, stick them in the comments on social or reach out to me, kevin@productionesp32.com. And I'll read all the emails. There's no AI processing of it or responses. If you hear from me, it's truly me.